Well, hello to all of you again and on the Zoom, and hello to those watching in the future. It is Semester 2, 2022, and this is the revision seminar for Data Analytics 1. I've had some requests, and I will do my best to talk about those things so that those of you, if you're watching in the future, you can't ask questions, but you can always go to the Maths Learning Centre and ask me what I meant. But you here who are live, you can ask me things. So if I say something and you want to know more about what I've said, please ask. If I write something down ridiculous like 1 + 1 = 1, please interrupt me and tell me immediately. Don't let me lose a minus sign and carry on for 10 minutes. That's ridiculous. Tell me straight away. But other questions, maybe wait till the end of the sentence and then ask me a question. I will stop every 5 or 10 minutes and just give you 30 seconds to breathe and ask questions. And if you ask questions that aren't directly relevant to what we're doing, I'll write it down and we'll get back to it later if we can. And sometimes I may have to think about your question for a bit before I respond, and I may have to ask you some follow-up questions to really understand what you mean. So just warning you, that's what's going to happen. This is your revision seminar. It's all about what you people need. So please, I am taking direction for you about whether what I'm saying is useful. So let me know, okay? All right. Right, so welcome. All right, I'm just going to do this example question with the probabilities and stuff and use that as a jumping off point. So probabilities with sample means. And I took a photo of it, so I'm just going to have a quick look. So I'm going to start off with an example and then riff off that to talk about the details of try and apply this to new things. Did I actually start the recording? Yes, okay. So that's example, even though there's no G in example, that's just how it's written. So two independent samples are drawn from two normal populations. Sample sizes are 20 and 25. Parameters are mu1 is 505, sigma 1 is 10, mu2 is 475, sigma 2 is 7. Okay, before I actually write down what the question is, I just want to understand what's written so far. So this is the setup, and then they're going to ask me to do something. So I have two independent samples drawn from two normal populations. So when they say population, they mean a collection of things or individuals which may or may not have exist yet. So when we say population, in our heads we normally think, oh, the population of Australia or the population of all Australian students or something like that, which exists already. But in most statistics situations, you're trying to predict stuff in the future. And sometimes the population doesn't exist. In quality control situation, you want to know like whether the toothpaste you've got have the right weight, and in your machine factory that builds the things, that produces toothpaste, and the toothpaste you're interested in doesn't even exist yet. So populations don't have to already exist. Sometimes they're just ideas that are going to exist when you actually collect the data. So I just wanted to say that there's a lot of philosophy in statistics. The Writing Centre coordinator would be happy to hear me say that because his research area is philosophy. So I have to say it at least once in every revision seminar week, philosophy, so just to make him happy. So just pointing it out that those normal populations might not exist yet, but the picture I have in my head is that I have one population. These are all the numbers it could possibly produce, and I shall call them x1, and these are all the numbers that x2 could possibly produce, and these are all different numbers that it could possibly make, and when I take a sample I'll get some of those numbers, but these are all the numbers it could be. And to say they're normal means that if I draw a height to say which ones are more likely than which ones, it'll be something like that, where it's more likely in the middle than it is on the edges. So this number is most likely to be near that number, and that's the mean, which is 505. And then this is spread out with like 10 that way and 10 that way to get to this point where it stops going down and starts going out like that. And whereas this one, the mean is 475, and the standard deviation is 7. These are very bad drawings, but they're enough. So this is what the picture is that we're going on with, that x1 could technically be any number at all, but it's most likely to be near 505 and even more likely to be within 10 of 505. Whereas this one is most likely to be near 475 and most likely to be within 7 of that. And the further away you get, the less likely it becomes. And being normal distributions, the percentage in this zone of the x2s is the same as the percentage in this zone of the x1s, because the standard deviation is a measure of how far, about percentage of stuff. So one standard deviation away from the mean, this zone has about 68% of the data. That's how a normal distribution works. And that's true for both of these. But look, this has 68% of the data spread out across 20, and this one has 68% of the data spread out across 14. So this one's narrower than this one is. Much more tightly packed, the x2s. Okay? I could attempt to draw them on the same graph, but I don't like my chances of that looking at all nice. I'll leave it at that. So this is the information I've got so far. This is what I've got here. So I've got the normal populations, and this here is these two pictures that I've got. And then what I've done is I've randomly taken 20 of these and 25 of these. And so since I'm taking 20 of these options, that it's much more likely to have ones in here. Most of them, there'll be some here and most of them in here. And some here and some here and most of them here. So I'll get 20 of these. And 25 of these. Okay, sweet. I don't know what's going on yet, but that's the picture in my head. You don't necessarily have to draw that picture when you do this, but I'm just making sense of what's going on here. How do people feel about what's happened so far? Cool. So the actual problem is find the probability that the difference between the two sample means, x1 minus x2, bar, is between 25 and 35. That's a lot of words. Okay. So the first thing it says is probability, and all probabilities are a comparison between the thing we're thinking of and all the things that could be. When you roll a die, you know that the probability of 4 is 1 in 6 because the 4 compared to all the things that could have happened is a sixth of the options. And so we want to know what's the probability of this number being between these two things. And so I need to think about being between these two numbers compared to all of the things that this could be, and how likely is it to be in this zone. Okay, so they have mentioned in their thing x1 bar and x2 bar. So x1 bar is the mean of this sample of 20 numbers, and x2 bar is the mean of this sample of 25 numbers. So I've got 20 numbers, and those 20 numbers together are producing x1 bar. Adding them all up and dividing by how many there are. So I add all these 20 numbers together and divide by 20, and that's what x1 bar is. And these 25 numbers, I add them all up and divide by 25, and that's x2 bar. Okay. And then I'm going to take these two numbers and I'm going to subtract them. That's how we got our data. So I got 20 numbers from this distribution and produced a mean, and 25 numbers from this distribution and produced a mean, and then I subtracted them and I got this one number. That's the story of what happened. So I have to imagine all of the answers that this could possibly produce and find out what percentage of those answers are between 25 and 35. That's what I have to do. Right, so first I should think about all the answers that x1 could possibly produce. So if I imagine all the possible ways of picking 20 different numbers and all the possible x bars that could possibly be produced by that process, that has a distribution of its own. And the word distribution means a description of all the things that could happen and how likely they are. So this distribution is also a normal distribution. And so these are all the x1 bars that could possibly happen. And the average mean is still going to be 505. So the individual x's, they are spread around 505, and if I take a collection of them, they'll still be spread around 505. And so the average is still the same as it was before. But when I take several numbers and I average them, they're going to be closer together than if I had individual numbers. And so the standard deviation is now going to be the old standard deviation divided by the square root of the sample size. So this is always true. So I'm just going to keep this diagram for later. So the beginning of this working goes x1 normal with mean 505 and standard deviation 10. x1 bar out of 20 is also normal, and the mean will be what it was before, but the standard deviation will be the old standard deviation divided by the square root of the sample size. How do we feel about what just happened? It's okay to say you don't feel good about it. All right. And the same will happen with x2 bar. So x2 normal with mean 475 and standard deviation is 7. So x2 bar, which was from a sample of 25, will also still be normal, and it will have the same mean as it did before, but the standard deviation will be less. It will be divided by a square root of 25 because that's the sample size. Okay, so that's the story now. So technically, there's actually like 20 of these that I've chosen a different one for each of them. So lots of different numbers here. And so only one of these is my actual x bar that I calculate today. But these are all the things that it could possibly be, and this is how likely they all are. And these are all the things that x2 bar could possibly be. And now I'm going to subtract them. Like that. So if I think of all the things that this could possibly be and all the things that this could possibly be, and I do this one minus that one, sometimes this one will be more than that one and you'll subtract them one way and you'll get a positive, and sometimes this will be less than that one and you'll get a negative. And there's all these different options for what the answers could be. And so when I think of all the things that x bar 1 bar minus x2 bar could possibly be, that will also be a normal distribution. So these are normal distributions, and I combine one of these numbers with one of these numbers. There's all these different options, but it's much more likely to get a number near 505 minus 475. Because the most likely thing that x1 bar could be is this, and the most likely thing that x2 bar could be is this. So the most likely thing that you could get when you subtract them is 505 minus 475. So these are all the things that could possibly happen when I did this entire process. So if I start here and have 20 of these and 25 of these and find their averages and subtract the averages, these are all the things that could possibly happen. And this is also a normal distribution. I know what the mean is. It's that one minus that one. It's the standard deviation that's tricky. Okay. I'm going to write that down. This will also be normal, and the mean will be this mean minus this mean, which is 10. But we also need to figure out the standard deviation. Yep. Oh, that's not 10. That's like crap ass. It's not 10. I thought it said 495. I'm really in a bad way this afternoon. 30. Much better. Thank you. Never trust a mathematician to do mental arithmetic. 30. 30. Yes. Yep. The question is the standard deviation. You can't just subtract the two standard deviations. So the two standard deviations we have are this number and this number. You can't just subtract them. That's not how standard deviations work. Standard deviations add together like Pythagoras' theorem from geometry. It's the square root of a squared plus b squared. Like that. So we take this standard deviation, which was that, and square it, and this standard deviation and square it, and we add them together and we square root. The fact that this is a minus is irrelevant. It's still going to be a plus, because when you square a minus, it becomes a plus. How are we feeling?
So the 10 and the 7, those were the standard deviations.
They were the standard deviations of the original x and x1 and x2. Back here.
So you don't put the variances in.
You can put the variances. It's the same thing. So you could have said the variance here is 100, and the variance here would be 100 divided by 20, which is 5. That probably would have been easier. Good move. And you could have said the variance here is 49, and this variance would be 40 divided by 25. You could have said that. That's a possibility as well.
But in regards to the formula that you just...
In the formula, the variances will add.
Yeah, but you... So like which one do you...
It doesn't matter. So you've got two options. You either square the standard deviations and add them and square root them, and that gives you the standard deviation, or figure out the variances and add them And that gives you the variance.
without the square.
Yep. And then if you want the standard deviation, you're going to have to square root. (49 on 25 would be that's what calculators are for. I can't be bothered. So that's what the variance is, and so the standard deviation will be the square root of that. But you could have done the standard deviation is the square root of the two standard deviations squared added together, and it would have given you the same answer. Yep. Oh, there was a thing in the chat. All right, I'll add that to the Blackboard, Chloe, while we're being quiet for a minute and letting people process. Okay. So what's happened is they've combined two things together. If you have a normal distribution and you create a mean from a sample of that, then the new mean will be the same as the old mean, but the new standard deviation, the new variance will be the old variance divided by the sample size. Or you could do the old standard deviation divided by the square root of the sample size. It's the same process. And then once you've got two normal distributions, we've got this one and this one. When you subtract them, you have to add the variances. If you add them, you would also add the variances. So that's the way it works. Yep. And so now we have that the x1 bar minus x2 bar is also normal, and it's it has this mean and this standard deviation, which is somewhere between through 2 and 3. Approximately. So now we've got this. So my x1 bars minus my x2 bars is most likely to be somewhere between like 25 and 35, between 27.5 and 32.5, approximately. So what we want is to know how likely is it to be between 25 and 35, this zone here. So if we imagine all of the x1 bars minus x2 bars that could possibly happen, how likely is it for them to fall up in this bit here? And that's going to be, I reckon, almost all of them. Because it's nearly, maybe 90% of them, nearly 2 standard deviations down and 2 standard deviations up. So that's nearly 2.5. Gone down 2 lots of 2.5 and up 2 lots of 2.5. Like 95% of them are going to be in that zone. But I need to do that exactly. I'm going to have to look it up in a machine that can do normal distributions or in a table. How does your lecturer like to do that sort of thing? Tables? Of course they do, because we can only do economics in ways that were done 100 years ago. Yep. So, if I was using a computer, I could directly ask it the question that I want to know now. So I want to know, what's the probability that x1 bar minus x2 bar is between 25 and 35. That's what I want to know. In this course, do they call this just P? That's the probability I want to know. And if I had a machine that could do normal distributions of any mean and any standard deviation, I could do this. I want to know this area here. That's the area I want. Now, a computer will usually only be able to tell you the left-hand side of it, and so you'd figure out this side, that bit, and go, all of this minus that bit is the bit I want. That's what a computer would do. But we don't have a computer. We don't have a table to look up something with a mean of 30 and a standard deviation of 2.63818, 2.63818. So I'm going to have to convert to a normal distribution that I can look up, which is the Z, like the standard normal distribution. So I'm going to have to subtract the mean and divide by the standard deviation to turn it into a Z. Running out of space there. That calculation is what I'm going to have to do. I'm going to subtract the mean from all three parts and divide by all three parts by the standard deviation. And when you take any normal distribution and you take off the mean and you divide by the standard deviation, it produces a Z. And this, whatever this is the thing we're actually going to look up. This is what calculators are for. Minus 1.895 and plus 1.895. How are we feeling? Cool. Whew. It's a big one for a multiple choice question. Okay, so now I need to go look this up. So now we're looking at Z, which has a 0 in the middle. And I want this area here. So I will find a book that has a normal table in it. This is the business statistics book. I think this is your textbook. Could be wrong. You've got a newer version that's online and it's got all that online stuff. So I've got, okay. So here's my table, and you'll see it has coloured in the left-hand side. And over here, it's coloured in the left-hand side here as well. So it only gives me the left-hand side of a number. So I've got the right-hand side of this and the left-hand side of this. I'm going to have to think of it in my head as this area minus this area to make the bit in the middle that I want. Or I could possibly just figure out this area and take off two of them because it's the same number and it's symmetrical. That's a different way of doing it. Because your normal distribution is perfectly symmetrical, so this area is the same as this one. So if I figure out this one and take it off twice off of 100%, that'll give me the percentage in the middle. So I get to choose, you get to choose how to do it. So let's see, the probability that Z is less than minus 1.895. Is this does this table look familiar to you? Yeah. So minus 1.8 there, minus 1.89 is there, and minus 1.89, oh crap, it's going to be halfway between those two numbers there. So pick one, or round it off to the nearest two decimal places because that's what your table has. Let's do two decimal places, yeah. 90. There we go. So minus 1.89. The area below it is 0.0294. Yep. From the table. And that's this bit here. And so I reckon I'm going to say that the probability that Z is between minus 1.90 and 1.90 is going to be 100% minus 2 lots of that number. Because based on my picture, it'll be 100%, which is all of it, minus those two numbers. And since it's in decimals, 100% is the number 1. Oh, crap. .9412. Right. So that's the probability we want. Is that one of the actual answers? Yay. That's always good. Yep.
I just had a question that kind of has to do with this. So if the population parameters weren't given, we had to use a t-distribution instead. And just hypothetically, if we got a t value that corresponds like 1.89, how would we find that on the table?
Your table doesn't give you probabilities, the t-table. So I'm just going to say that aloud for the people who are listening, who aren't in the room. So you're saying, what if you had to do this and you didn't know the real standard deviations and you had to approximate it from the sample standard deviations? So if here we didn't know what sigma 1 was, but it was S1, and this was S2, then our then that would mean that when you got down to here and did this calculation here, it would turn out to be a t and not a z. Technically, we don't actually know what any of the in-between distributions are, but we do know what this one works out to be. It's a t. So, and then you're saying, how do you, with a t distribution, so what if it was the probability that what if it was like that, you're asking?
Yeah, but let me just like rephrase it a bit, because like what you previously did with this is look at the table, and on the left hand side you got your first digit, you got your second digit, but for a t distribution table, like on the left side it's just degrees of freedom of the significance value.
Yep.
And we've been taught how to calculate degrees of freedom and do the alpha G-table stuff, but I don't know how to. So let's say we get 1.9.
Yep.
How do we find the probability?
Yep. So how do you find the probability from the t-table? The answer is you can't. So there isn't a table like this for t, because there would be a different one of these entire tables for every degrees of freedom. So the best you can do is get an estimate. So you can say, if I was here at degrees of freedom 43, for example, that's what it would be in this situation. I would go down to the nearest row I can, which is 45, and I would go look for my 1.8. Ow! Sorry. Oh, that hurt. Just whacked my knee on the bench. Oh. All right, so here I am in row 45, and my 1.8 is between these two numbers. right? My 1.9, sorry, is between these two numbers. And I go back up here, and the probability on the outside is between 10% and 5%, which means the probability on the inside is between 95% and 90%. But I don't know which one it is.
So for a hypothesis test, if it was had to deal with the t-distribution, it would be easier to conclude by using the t-values rather than the 0.5, 0.05.
Yeah, well, you would know that it's between, the p-value would be between 0.05 and 0.10.
Yeah.
And so if the significance level is 5%, you reject. Yeah. So I'm just going to actually officially answer the question. The table says that between 1.679 and 1.679 is 90%, 95, yep. And between minus 2.042 and 2.042 is 95%. And so this probability is between 90%, well, crap, I should be doing them as decimals, shouldn't I? Because that's probabilities. 0.90 and 0.95, but I don't know exactly what it is from the table. If I had a computer that did t-distributions, I could get it exactly. Like I could go to Desmos and ask it what the t-distribution formula is, and it will get an exact probability. And Excel can do it too. You can go t.dist and ask it the probability. But because there's a different t-distribution with different list of probabilities for every degrees of freedom, you would have to have a whole set of pages of this table to do what you want to do. Yeah. But we do know that if we were doing the outside, it would be between 5% and 10%, and so we'd get under more than 0.05, so we'd normally retain. Yeah. Okay. So, person who asked me this, how are you feeling? No, he's not paying attention. How are you feeling? Oh, no, just this problem that we just worked out.
No, you explained it really well. Like,
Good.
I just experimented with the values and I'm really confident. And I think with the t-table stuff as well, I think, because I sort of ran the past exam stuff a bit, it's more so just knowing when to apply like the full variance test. And because the formula is so complicated, you never really actually do it with the t-test.
Yep.
It's just a matter of now I feel like you can do it with the Z method, which might be asked. But no, very good. Thank you so much.
Cool. So this question is not technically about t-tests or z-tests. It's the theory behind why those tests work the way they do. So the theory behind the two-sample t-test is based on this sort of reasoning, saying, well, in this situation, this thing would have a distribution of this much, and this thing would have this kind of distribution, and then you subtract them, and that would have this kind of distribution. So you spend a lot of time doing calculations on different kinds of distributions. And they call these sampling distributions in most courses, where it's saying, well, this is the distribution of x, and this is the sampling distribution of x bar. But it's really just, the word distribution is just the description of all the things that could have been and how likely they all are. And normal distributions come up, and so they're really famous. I'm just going to check something. Did they do the binomial distribution in this course? Okay. Cool, just checking. So that is a distribution of counting how many events happen out of a collection, as opposed to measuring things, which is what the normal distribution is. Okay. Cool. Let me talk about these null hypothesis and significance and stuff. You're going to have to help me. Every first year statistics course has a different list of what hypothesis things are in it. So all that stuff. So I'm just going to have a check. Did your lecturer talk about p-values and like critical test statistics? Yeah.
I just wanted to add, like could you, like later on, could you go over contingency tables and additional probabilities?
Okay, we can give that a go. I'm going to write on the board or I'll forget. Let's see what I can get through. All right. So just remind you that for those of you who are here live, the Maths Learning Centre is open all week. So if you want to talk about any of these things that I don't get to, then there's people to talk to about it. Okay. So, right. A hypothesis test, or a significance test, depending on what they're called in this course, is a way of making a yes or no decision using probabilities. That's what it's for. That's the purpose of a hypothesis test. So every hypothesis test is helping to answer a yes or no question. And that yes or no question is usually concerning a number of some sort. But I'm just going to say it doesn't always concern a number, and sometimes it concerns two numbers, and sometimes it just is just a yes or no question of something like, are these things related? So I would like to check some details. And you're going to have to help me here because the notation and the terminology will be a little different in every course. So, we're just going to do a brainstorm. We must have done hypothesis tests concerning means because you talked about t-tests. Is that right? And did you do a t-test we did t-tests that had compared two means, and we did ones with pooled variance and ones without pooled variance. Is that right? Two means, then we had pooled. Not pooled. Stuff it. I'm just going to tell you the state of mind I'm in. The word pooled is in a quote from Barbie and A Christmas Carol. And Barbie says, "But the butter is pooling, Catherine." Sorry, I just had to get it out. I have to say, when I see the word pooled, I have to say, "But the butter is pooling, Catherine." Sorry, it's from a Barbie movie. Do you know the Barbie movies are the movie franchise with the most movies in it out of all possible movie franchises that exist currently? Sorry. Even more than Disney. Sorry. I've been doing revision seminars all day, so I'm reaching a very strange state of mind. Okay, so here we are. Did you do ones that were about a single mean being equal to a particular number? And you did ones where some of them were Z's and some of them were T's? Okay. And did you do the paired t-test? Does that sound familiar? No? Okay, cool. It's okay. I just need to be sure because some courses have that. That we're paired meaning joined together in pairs. No? Good. Makes my life simpler. Okay. So what about proportions? Did we do stuff with that? Did we do ones with like a single proportion, like the null hypothesis, like p equals 0.8 or something? That sort of thing? And that was a z, I think, if right. And did we do one with two proportions? Actually, I know we didn't because someone came to the Maths Learning Centre extremely confused about one of those online questions, and it talked about two proportions, and it wasn't in the course, even though it was in the textbook. So no, we didn't do two proportions. So no. Now, have there been any other situations in which you calculated a test statistic or found a p-value or something? That's it? What's that? Yep. So all of these things had p-values. Do we have any others? Like we've got with two means, with pooled and not peen, we've got a single mean which comes out as a z or a t. We've got proportions with one proportion. Anything else? That seems it. Can I ask a question? Did we do a chi-squared test? Nope. Good-o. If you don't know what that means, you wouldn't know. The Greek letter chi, chi-squared test. Nope. All good. This is much shorter than the list used to be in this course. And I have one more thing. Did you look at p-values that go with regression or only the SST, SSE stuff? There were no p-values that happened in regression? No t-statistics in regression? Good. Yeah, I just needed to check. Other statistics courses and this course, like 3 years ago, had other things in it that are not in it now. So I just wanted to check. Okay, sweet. I will talk about only these things. If you come up with another one later, all good. Can I just say something? For the purposes of studying for an exam, it's a really useful exercise to sit down and try to remember all the things in it without looking, and then look up to see if you missed anything. Even, do you guys get to take notes into your exam? How much notes? One side? Why would you do one side? Then you have to collect them and check. Oh, anyway, sorry. One side. Great. I'm just going to deal with that emotion. The research into cheat sheets says that it doesn't really matter, and so you should let people have two sides. Like, cheat sheets serve the main purpose of just making people feel better. Like you can look and you can know that if you forget something, you can look it up, right? And it just makes you feel safer to have one. And so if it's all about safety, give people two sheets, two sides. Anyway, moving on. Okay, cool. So one way of picking the best things to put on your cheat sheet is to try to remember stuff and put the things on the cheat sheet that you can't remember. Because the things you can remember, you don't need on there. If you have to make a decision because you haven't got enough space, because there's only a limited amount of font that you can read. If you haven't got enough space, you can cut things that you can remember. So yeah, anyway. So that exercise we just did where we tried to remember all of the different situations in which we calculated test statistics was really useful, because then you can go and check what was missing, and remembering things and being wrong and fixing it is really good for your brain. So there you go. Okay, so let's talk about all these things. So, just going to try and organize these. Right. Is that a clock? What is that? Yep. Maybe it's just water dripping from above. That's not unlikely in this building. Okay, I'll cope. So we have all of these different situations in which you can do tests, and they are all similar in some ways, but different in, as you've noted, extremely technical ways. So I'm going to organise them by the question that they answer. Is the population mean equal to this specific number, insert number here? So that would be a classic quality control question, which is something like, my factory produces ice cream and it says that there's 2 litres of ice cream in every tub. I measure ice creams and the mean was 2.1 litres. Is the true population mean of all ice creams that my factory could possibly produce 2 litres? That's the sort of question you could ask. Okay. As 2 litres, I measure. Pick a number. 60 tubs, and the mean was 2.1 litres with a standard deviation of 0.8. Is there strong evidence that the mean is not 2 litres? That's the story that I'm making up today. So this is the tub says that it has 2 litres in it. I should show you a tub of ice cream. A tub of ice cream says it has 2 litres. And so that's what I'm wondering, if the population mean really is 2 litres. And so this is the question that we're trying to answer. The null hypothesis is that the mean really is 2 litres. To choose a null hypothesis, you have to choose a number like a population number, like a parameter in the population, to be equal to a specific number. All null hypotheses are able to be pitched that way. And so, is this how your lecturer writes this thing, H naught, like that? Something like that, where mu is the population mean volume of a tub of ice cream. So you're supposed to, every time you write down a symbol, you're supposed to tell the reader what it stands for. And so they don't have to detail what H naught stands for, but they do have to be told what mu stands for today. So mu doesn't stand for the number 2, mu stands for whatever the population mean really is. And I'm wondering, is it 2? And the alternate, does he call it HA? Or H1, HA? God forbid we'd be consistent. So HA is that it's not 2. And it specifically says is not. If my factory owner was wondering if he was overfilling his ice cream tubs, he may be wondering if the mean is more than 2 litres, which would be a greater than in this spot. Yep.
There were some questions where it's phrased like, yeah, they give you the population mean, and your sample mean was sort of like greater than the population mean. Does that automatically make your alternative hypothesis greater than that?
Oh, does the way that things are described as, sample mean being more than, does the sample mean being more than the population mean automatically make it greater than? No. So mine is more than, but the question was, is it not 2 litres? Which means it's still two-sided.
So as long as once I see it's not, like that's a keyword.
That's the key word for two-sided. This distresses me a lot because things should not be based on keyword strategies, but that is how to survive in these exams. If they want it to be one-sided, fingers crossed, they will be clear about the fact that they are interested in it specifically being more than or less than. So they will make a phrase, something like, the factory owner is wondering if they're overfilling their tubs. And you go, oh, we only care if it's more than. Yeah. Okay. And then we're going to say that X bar, it's traditional to call it X bar. Is that how your lecturer does it? Yep. Is 2.1 and the standard deviation is 0.8 from the sample. We don't know what the population standard deviation is. It hasn't mentioned it anywhere, so I can't use that fact. But I will just do a what if it was a population standard deviation. So this 0.8 is implied to be from these 60 tubs because it's in the same sentence. And so this belongs to the 60 tubs, so it's a sample standard deviation, not a population standard deviation. And so since it's a sample standard deviation, that means we're going to use a T and not a Z. So what I'm thinking that since it's a sample standard deviation, I'm going to use a T and not Z. That's the decision between those things in this context. But if they had specifically said, ice cream tub says it's 2 litres, factory owner believes that the standard deviation is 0.8, then you would say, that must be a population standard deviation. Because it was mentioned about all possible tubs, it wasn't about the sample. So you're noticing here that success in statistics questions is at least a certain amount about grammar and reading and not about mathematics per se. Yes?
Are there some scenarios where it's kind of like debatable which one it is?
There will be scenarios where it's debatable, but if your lecturers are at all reasonable people, they will make it clear in the exam. So almost always in real life, you don't know what the real standard deviation is. And so in real life, you almost always just use a T. But you know how I said that they like to do statistics in 100 years old ways? The t-test was invented in about 1910. And in 1920, it was still new. And so people really believed that you had to learn all about the z-test before you learned about the t-test. Well, economists still believe that. It's not a bad thing, but if I was going to cut something from a stats course, it wouldn't have been the two proportions test, it would have been the z-test for, if I had to choose, I would have cut different things. But anyway, it's really hard to write a good statistics course. Statistics education is a basket case worldwide, and almost everyone anywhere complains about it, which is why we have a Maths Learning Centre. So I'm going to use a T and not a Z. Okay. And so let me just stop for a moment before I finish this and talk about the philosophy of this. We're going to have to try and make a yes or no decision using probabilities. And my yes or no decision is deciding between these two options. And I have to calculate a probability. What I have to do is I have to look at the numbers I have from my sample and decide how unlikely they are. And if they're really unlikely, then if I did live in this land and I knew this was true, and I thought, if that was true, how likely is this to happen? And it was really unlikely, then maybe I would believe that this isn't true after all. It's a proof by contradiction using probabilities. So if this is true, that would be unlikely, and so I don't believe this. Or if this is true, this is totally ordinary, and so maybe this is true after all. That's the sort of idea behind it. But there's too much information here. There are too many ways for this X bar to happen, and I can't figure out what the probabilities that go with this X bar are. And what the people back in the 20s figured, 1920s, 100 years ago, figured out was that if they do this calculation instead, then they are able to imagine all of the things that t could have been and compare what I've got to those. And so the reason we've chosen this t is because the probability theory says that I can look this up in a t table. Whereas I have no table to look this up in, but I do have a table to look this up in. That's why we're doing what we're doing. And so this t statistic, so the formula for t is the x bar minus the mu that goes in the null hypothesis, s on root n. That's the formula, I think. And this comes out to a particular number, which is exactly what calculators are for. 2, well, I know what 2.1 minus 2 is. 2.8. So my calculator says that's 0.968. All right. And so now I have to say, all right, this is the number I got from my sample. If this null hypothesis was true, how likely would it be to get a number this big? How does this compare to all the t's that could have happened if I had been in this situation and collected this data another time? If I imagine all of the times I could possibly collect 60 tubs and find their mean and their standard deviation and do this calculation, imagine all the things that could possibly have happened. What are those options? And those options are a t distribution with n minus 1 degrees of freedom. So So 59 degrees of freedom. And that is what Gossett figured out when he was working for the Guinness Beer Company in the 19-somethings. I don't know the year. It was before it was before the First World War. That's what he figured out. He didn't call it T when he invented it, but he called it Z, but then everyone else said, we've already got a Z, we need to do something else. And so here we are. And so we have to go look that up to see how likely it is. So here is all the T's that could possibly have happened. And here is all how likely they are. It looks like a normal distribution, but it isn't. It's a little bit different. But to the naked eye and to the crappy drawing on my paper, it looks like a normal distribution. It's got a 0 in the middle, and mine is here-ish. I don't know exactly where it is. And I want to know, how likely is it to be this far from 0? That's what I want to know. Because the most likely thing to happen, if the mean really was 2, would be to get a t being 0. But mine isn't 0, so how likely is it? And so I'm going to figure out how likely it is to be here or further. And since I would be just as surprised if the mean was less than 2 as I would if it was more than 2, I have to do this side as well. So that total area, that's a probability. I want to know what percentage of the area that is. So if I had a computer, I could literally ask it, tell it the degrees of freedom, tell it these numbers, and it would give me the answer. But I don't have a computer. I've only got a t table. So let me go look at the t table. I really shouldn't have lost it. So I presume they're going to give you t-tables in the exam. So here's my t-table. And I'm going to come down here and I'll find 59. 59 isn't on the list, so I'll just use 60. So I'm going to use row 60. And the probability that t... All right, so what row 60 says is that to have 10% on the outside, these two sides here, have 10% out there, the t would have had to be 1.296. And to have 5% on the outside, the t would have had to be 1.671. And my t is further in than this one. That's what that says. This is the absolute value of t is greater than 1.29. Have they used this notation in this course? No? That's all right, don't do that. So if the t had been exactly 1.296 from the table, the p-value would have been exactly 0.10. That's what would have happened. But mine is further in, so the p-value is bigger than that. So this is the critical t over here, 1.296. That's what it says in the table. And it says that if it had been 1.296, the p-value would have been that. And so therefore, the p-value must be more than 10% because mine's further in, so the area is bigger. Alternatively, you could just not talk about p-values at all and just say, so that's the thing, row 60 in the table, the critical value for 0.10 is 1.296. The calculated value of 0.968 is less than 1.296, and so therefore we're going to retain the null hypothesis. Oh, do they say retain or do they say do not reject? The revision seminar before this, they say retain instead of reject. Well, do not reject. So.
Is the critical level inside of
it is. So I've rejected it. I haven't rejected it at the 10% level at the moment, but I could have looked at it at the 5% level as well, and that would have been fine as well, because I've used the 10% level. It's tradition to use the 5% level. If you don't reject at the 10% level, you're guaranteed to not reject at the 5% level either. Yeah. So either of those arguments would have worked. So, yep.
So I did the sample test, and one of the questions was saying something along the lines of what happens when you increase the significance level, or just different terms.
So
what does that mean? Does that mean that the number is it's like going down, or?
So the significance level is the cutoff for where you declare a p-value to be low. So a p-value tells you how likely this is, and if it's unlikely, you'll say, I don't believe the null hypothesis. And so if your significance level is a small number, then it will be harder to reject the null hypothesis.
Yeah.
Yeah.
So, but when it says increasing the levels, does that mean that your p-value is small?
No. The significance level is the percentage for the p-value where you would decide whether the p-value you actually got was more or less than it. So if the significance level was 10%, that's not saying your p-value is 10%. That's saying that whatever p-value you get, you compare it to 10% in order to make your decision.
Yeah.
So if they say, if you reduce the significance level you would still get the same p-value, but you might make a different decision about whether to reject or retain.
Yeah, I know, I understand that. But
Yeah.
when it says decrease the significance level, does that mean like instead of 10%, be like 5%?
Yeah.
Oh.
Yeah.
Was that significance level like 10%? Was that given in the question?
No, I just made it up.
Default into that?
I just made it up. It was because my first instinct was to try and figure out what the p-value was. Because in the course that I was taught statistics, we never used straight up critical values. We always converted to p-values. And so my first instinct is to say, well, if it was 1.296, the p-value would have been 10%, but t is actually 0.968, and so the p-value has got to be more than 10% because it's further in. And so since the p-value is more than 10%, I would retain at both the 10% and the 5% level. And so then I would go and look at the question to see what level it suggested. But since it didn't suggest a level, I would say I retain at both the 5% and the 10% the significance level.
So if the p-value is less than the significance level, HO is rejected.
Correct. So p-values being small mean that you think your data is unlikely, which means you don't believe the null hypothesis, so you reject it. So p-value too small, i.e. less than the significance level, that means that you reject the null hypothesis. Yeah. That's what you said, wasn't it?
Yeah.
Yep, and that is the truth. And if the p-value is too big, meaning it's more than the significance level, then you don't reject the null hypothesis. Because you're going, well, if the null hypothesis was true, the probability of this is, 20%. That's totally normal. That's ordinary. Could totally happen. So, yep, could be the null hypothesis could be true. I have no evidence to suggest it's not. And that's exactly how we talk about it. If it's too small, you say there is strong evidence to suggest. Well, if it's under 0.05, you normally say there's strong evidence to suggest that the null hypothesis is false. And therefore, the mean isn't 2.
Do we ever say we accept one option?
Nope.
Do we always say fail to reject?
In this course, officially you say you fail to reject. And you might say we fail to reject. So in this case, we fail to reject the null hypothesis and conclude that the mean could be 2 litres. But even then, I still haven't said it is 2 litres. It just could be. Yeah. I don't know how annoyingly precise they are in this course.
MCQ.
Oh, it's MCQ? Yeah. So usually you in statistics, you're never 100% sure of anything. And so if one option is the mean is 2 litres and the other option is we don't reject that the concept that the mean is 2 litres, you'll do the we don't reject, because that's the one that is less sure. Yeah. Yeah. Okay. Cool. So those steps are part of any hypothesis test where you set up the hypothesis in terms of some number, which is usually the mean, which is often a mean, and then you set up a test statistic, and then you compare your test statistic to the distribution that it could have been, and you either say, well, this is the critical t that would have given me a p-value of exactly 0.05 and mine's further out, so I reject, or this is the exact p-value and so it's less than 0.05 and so I reject. Or whatever the significance level is. 0.05 is a tradition because Fisher first used it when he invented them in the 1920s. Or no, must have been earlier than that. I really must look up the dates. All of this stuff happened between like 1890 and 1930. Whatever. Fisher actually was a lecturer at University of Adelaide. And then he died of tuberculosis. So, and he also refused to explain anything that he thought was obvious. He was famously smug. Yeah, so I try not to be Fisher. A, I don't want to die of tuberculosis, and B, I don't want to be famously smug. Okay, so there's that one. But what if instead of doing the sample mean, it had said it's known that the standard deviation for all tubs is 0.8 litres. That would be a population standard deviation. And in that case, I would have said that x bar is 2.1 and sigma is 0.8 and not s. And that would have said to me that I'll use z and not t. But all the rest would be the same. And so I would do z is x bar minus the mu naught divided by sigma on root n. And that would be for us 2.1 minus 2 on 0.8 on root 60, which would have given us the exact same answer. But instead of looking it up in a t table, I'll look it up in the z table instead. And so you can either go and look up this exact number and get the correct exact p-value from the z table, which you could do. And so I'll do this bit here because the table only gives me the left-hand side, so I'll figure out this bit here. So in the z table, minus 0.97 is 0.1660. Crap. There's 0.9, minus 0.9, and there's 7 there, 0.1660. So the probability that z is less than minus 0.968 is 0.1660. And so therefore the p-value will be 2 times that because this is only half of it. Yep?
How does the, whether or not it's two-tail, one-tail test, how does that affect the p-value? Because I know you like divide by 2 or something.
Yep.
I don't know when.
So the one-sided, so we've got a two-sided one because it's a not equal. And that means we have to use both of these pieces. The z table can only tell me one of them, which is this one. But the p-value is both of them, both tails. So I'm going to have to times this answer by 2 to get the actual p-value. That's what makes the decision. I mean, even before I times it by 2, I would have retained the null hypothesis because this number is gigantic already.
So it doesn't actually change.
Well, sometimes it does. So if this number came out as 0.027, then if you're only using one side, that would have been under 0.05.
Yeah.
But if you're using 2, timesing it by 2 would have bumped it up above 0.05, and you would have not rejected. So it only matters if you're close to half of the 0.05. Yeah. So we don't reject at the 5% level, but we don't reject at the 10% level either because it's really big. We don't reject at the 1% level or the 10% or the 30% level. Like, yeah. So the difference is that these two tails means that I have to colour in both halves. And the table only gives me one half, and so I'm going to have to times by 2. or in the T table, it'll either tell you to which one is whether it's one or two sides, and it'll give you both. But you'll see the one-sided one is always half the two-sided one. The two-sided one's always twice the one-sided one. And that's because this two-sided one is literally two of these things coloured in compared to one of them. When I learned first year stats, they didn't do one-sided tests because they thought it was just too much extra to add to the pile of things to do. We only did two-sided tests, and so we never had to worry about which one was which. And I feel sorry for all of you. Also, my lecturer explicitly said they didn't believe in one-sided tests. Exactly because of that problem of suddenly switching from reject to retain when you go from two-sided to one-sided, and going, well, if your problem is able to switch from reject to retain just from that decision, maybe it wasn't a very good problem. So just do two-sided all the time, that's what she would say. And I believe in her, but you have an exam to do written by people who have a different belief. So this is the game you're playing. In your future, if you ever do statistics, you can always do two-sided tests if you like, but for your exam, unfortunately, you do not live in that future. So, yeah. So far, we've had two of them, and I know that I'm pushing the time that I'm supposed to finish, but that's okay. So far, we've had two of them. We've had a Z test and a T test for assessing the exact same question. The question is the population mean equal to this number? That's the question that we're answering, and both of these answer the same question, and the thing that distinguishes between them is that in the Z, we knew the population standard deviation, and in the T, we didn't. We only knew the sample standard deviation. So that's the decision between those things. So is the mean equal to this number? And we know the population standard deviation. That means I'm going to do a Z equals x bar minus mu naught on sigma on root n, and I'll use the normal distribution. But is the mean equal to this number, and we only have the sample standard deviation? That means that we'll use a T, and we'll use an S in there, and we'll use a T distribution with n minus 1 degrees of freedom. So far, these are the two things we've talked about, and that's how they're similar and that's how they're different. When you have to make decisions between things, you need to know what piece of information distinguishes between the two different decisions. And for us, the only thing that distinguishes between these is these two things. Do you know the population standard deviation, or do you only have the sample standard deviation? In real life, this would never happen and you'd always do this. But as we've discussed already, your exam is not real life. No exam is real life. Exams are some weird ass upside down. So, okay. So I've dealt with these two for a single mean. I'm going to switch it up and ask us one more question about a single number. And that is, what if instead of asking is the mean equal to a number, where every individual object has a number recorded about it? That's this situation. Every individual object each has a number, okay? What if you're in a situation where every individual object doesn't have a number but only has a yes or no, a category that you've put it in? Is it, so for example, you could say, do more than 50% of people participate in volunteer work? That's a question you could ask. And that number there is a percentage. And when you think about each individual person, all you have is a yes or no. Do they participate in volunteer work or not? So it's useful to be able to do that, to say the individual things or people that it's talking about, do they each individually have a number, or do they only have a yes or no about each individual one? That can help to make the decision. So each individual has a yes or no, and then you ask, is the proportion of either yes or no, it doesn't really matter which one it is, equal to a particular number. That situation. That's different to this situation, because in this one, each individual has a number recorded to them, and you're asking, is the mean equal to something? But this one, each individual just has a yes or no, and you're asking, is the proportion equal to something? That's how they're different. But they're similar in the sense that there's only one number you're thinking about. So this would be an example of something like, just a second, let me think about this. Just wait. A researcher was interested in whether more than 60% or 50%, let's just say a majority, they're not a researcher, they're a marketing team. Marketing team was interested in whether more than 50% of people would buy their new product. They surveyed 100 people, and 58% of them, let's not say 100, let's pick a weird number. 92, yeah, just to make it interesting. And 58% of them, or maybe we can't have 58%. Let's just give it a raw number. 53 of them they would buy. Okay, I'm not going to actually give a question here. I'm just going to run with what the information we've got. I'm just going to make up the question. So this is a situation, and we are interested in whether more than 50% of people would buy their product. Now, they've specifically said that they are interested in whether it's more than 50%, not whether it's equal to 50%. But 50% is the thing we're interested in. And so we're going to say that the null hypothesis is that the proportion of people that would buy the product is equal to 50%. And the reason we have to say equal is that we can't do any of the calculations unless we pick a number. And the alternative is that it's more than. Oh, so traditionally it's not a percentage, it'll be a decimal. Like that. You do it as a decimal, not a percentage. So is the proportion more than 50%? That's what we're interested in. But the only way to do the calculation is to pick a number. And so we'll pick the smallest number. We'll pick the first number that isn't in this, which is 0.5. So technically it should be this. But that's not how it's done. So the null hypothesis has to be about picking a specific number, and 50% is the last number we're interested in. Everything above that is good. Anything below that is probably bad. So that's our cutoff. So that's our null hypothesis. This is a one-sided hypothesis test because we're only interested in whether it's more than. And so we are going to now try and figure out what's going on. And we have to say P is the true proportion of people who would buy the product. So we set up the null hypothesis, and now we have to create a test statistic based on the information we've got in our sample. So when you have a mean, it's mu, and the sample mean is x bar. Well, when you have a p, it's a proportion, it's p, and the sample proportion is p hat. That's right, isn't it? Do they use a p with a hat on the top? So we had 53 out of 92 people. That's going to be my 3 to... Should I do more decimal places? Let's do one more. Okay. Just in case. So that's my sample proportion. So 57.6% said yes, they would buy in my sample. And I want to know if this is evidence that all people have more than 50%. Now, even if the percentage was exactly 50%, can I change it to 60%? It will tell me something. It'll be... I'm going to change it to 60%, sorry. The reason I'm going to do that is for reasons that will become clear. So you can't change your exam questions, but I need to do this so that there's a point that is easier to see with the numbers I've got. So I want to know, now it's retain. Curses. I really wanted to reject it. Can I change this number as well? All right, let's do that. Okay, sorry about that. When you're making up examples on the spot, you can't always set them up. So you can now see behind the lecturer curtain, so sometimes you choose examples and then you go, oh, that's not going to tell me the story I want to tell, so I'm going to change it to this. Okay, so it was 73 people. So the sample proportion is 73 people out of 92 total said yes, and so that's the proportion. Percentages would be 79.35%. Proportion is a decimal version of that. And so I need to know if this is evidence that the true proportion is more than 60. Even if the proportion was only like, even if the proportion was 90%, this still could have happened in my sample. And if the proportion was 60%, this could have happened. I just need to know how likely it is. So yeah, even if it was 60%, this could have happened. I could just accidentally have happened to choose a lot of people from the 60% that say yes. So I want to know how likely this is, and so the test statistic I'm going to calculate is this time a z. And I'm going to have my p hat minus the proportion that's in the null hypothesis divided by this thing. And this thing is the p naught 1 minus p naught over n. Pretty sure. Yep. No, I'm using z because it's always a z in this story. Yep, because I'm not... Let me just step back a bit. I am using z because of the amount of observations, but if I didn't have enough observations, I also wouldn't use t. Because this is a totally different situation. I'm not talking about averages where every person has a number. I'm talking about percentages where every person has a yes or no. Totally different situation. It just happens to turn out to be a z as well. And that's because the number of people out of 92 that say yes is a binomial distribution. And when you draw the binomial distribution, it looks like a normal distribution. And so when you calculate this thing, it will be approximately normal. And it is actually only approximate. This is not exact. If we really wanted to do this, we should probably use a binomial distribution, but there you go. So there is a check you're supposed to do. Is that better? There's a check you're supposed to do, which is you need both the number of people who said yes and the number of people who said no both have to be more than 10, which it is, so that's okay, in order for this to work. And otherwise, you haven't been taught what to do instead in this course, but you would do something else.
Is this like a Bernoulli trial?
This is very a Bernoulli trial. We have 92 trials of did they like it or not. And the success in this case is yes, they would buy the product, and failure is no, they wouldn't. And the probability of success we are imagining is 0.6. We don't know what it really is, but with the null hypothesis, it's 0.6. And so we are finding out what's the probability of getting 73 or more in this situation. But since the binomial distribution, imagine you're in 1920 and computers haven't been invented yet. You can't ask a computer what the binomial distribution probability is. So you have to convert it to something that you can look up, and people have been working on the normal distribution for a good 60 years now in 1920, and so they've made the Z table by now. So if I can turn into a Z, I can look up the probability. That's the imagining that we have. Okay, and so this works out to 0.7935 minus 0.6 over the square root of 0.6, and 1 minus 0.6 is 0.4 divided by the 92. So just note that it's always that way, that if the P0 was 60%, then the other bit would be 40%. It's the other percentage. And so if it's 0.6 and 0.4, or it would be 0.7 and 0.3, or it would be 0.9 and 1 and 0.1, or it would be 0.5 and 0.5. So if it's 0.5, then they're both the same, and I didn't want to give the impression that they were always both the same, which is why I changed it to 0.6, to note that these two numbers will work out to be different things. In the textbook, sometimes they call this thing Q, and sometimes they call it 1 minus P. And so my calculator now says that the Z statistic comes out to whatever this is. No, you can't see that anyway. So 0.79 0.7935 minus 0.6 divided by the square root of 0.6 times 0.4 divided by 92, and I get 3.789. Actually, the Z table's only got 2 decimal places. Let's go 3.9. Okay. And that number is huge. Most Zs come in the zone of from -2 to +2, and this one is very large. So here's my Z, 3.79. Because I'm only doing a one-sided hypothesis test, I will only do the right-hand side, because I'm interested in the greater thans. And the probability that Z is more than 3.79, let's go to the table here. 3.79 is 0.0001. Oh, sorry. I've actually done the probability of being less than minus 0.79, but it's symmetrical, so it's the same thing anyway. So that's a trick. You can look up the negative one and it'll work out the same. 0.0001. And that number is less than almost any significance level you would care to name. So we reject H0 at the 5% level and the 1% level if you want. So the point of doing a p-value is that you can let someone else choose what their significance level is. So if I tell you this p-value, you who like a significance level of 5% can say, yep, I reject. You who like a significance level of 1% can say, I reject. You get to choose. So even if they didn't tell you what the significance level is, doesn't matter what the significance level is, I'll still reject. And so I conclude that more than 60% of people would buy, assuming they're similar to my sample, got to be careful that I chose my sample randomly out of all the people I'm interested in. If I only asked like teenagers at a particular school, then maybe not. So we don't know that. So we just conclude this that more than 60% of people would buy the product. Okay. So that is the one sample proportion Z test. And the difference between it and these tests is that I'm not interested in a number for each individual. I'm only interested in a yes/no for each individual. And I want to know what percentage that is. But I actually don't want to know what percentage it is. I want to know if that percentage is equal to a specific number or not. And so I'm not calculating a mean by averaging everybody's numbers. I'm calculating a percentage by counting how many people were in a particular category. That's the difference. And as far as I know, that's the only proportions test you've been given. Pretty sure. There does exist one that compares two proportions, but you haven't been told that. All right. So I'm not going to do any more written specific examples of all the details for everything else, but I am going to talk about the situations that they appear in so that you can distinguish between them. So we've so far had only situations where there is one thing written down about each individual, and I want to know what the average is or what the proportion is for the whole population. What if you had two situations and you wanted to know whether the mean was different in those two situations? Is the mean different in these two situations? That's an important question that you want to know. And this is much more useful than the other ones. It's more like, yep, the mean is the mean of my profit when I have this advertising campaign. Is it more or less than the mean of the profit in this advertising campaign? I'm trying to design things that fit, clothing that fit people. Is the mean height of people in this country more or less than the mean height of people in this country? Those sorts of questions. You've got two different situations and you're interested in whether it makes a difference to the number that people have on average. That situation will have a null hypothesis of the mean in group situation 1 is equal to the mean in situation 2. That's traditionally how you'd write it, but you may see it as mu1 minus mu2 equals 0. They're the same thing. This one is officially about one number. I know it technically is about the two numbers, mu1 and mu2, but this is really one number. It's how far mu1 and mu2 are apart. Is it 0? And so this is the one that matches most closely with how null hypothesis tests are set up. It says, wait. I need to have a yes or no question that concerns a number. And I need to pick a number for the null hypothesis. And so if I pitch it this way, then the number I pick for the null hypothesis is 0. That's why they write it this way. But this is the thing that's in your head. Are the two means in the two situations different? Where U1 is the mean in situation 1 and mu2 is the mean in situation 2. And it's very important that all of the individuals that you measure in this story are different people or different schools or different days or whatever. You're not allowed to have two measurements on the same individuals. They all have to be different. They all have to be independent for the thing that I'm about to do to work. It is possible to answer this question by putting the same people in two different situations and measuring them twice. And that's what the paired t-test is for that I mentioned earlier. But you didn't cover that in this course. I don't think we did. Pretty sure. So anyway. All right. And the alternative is usually that they're not equal. Usually. But sometimes you are concerned with one of them specifically being more than the other. And that's one-sided. Okay. So theoretically, you could imagine being in a situation where you knew what both of the standard deviations were in the population in these two different situations. And you could do a Z-test for this. But people don't do that, and I'm pretty sure it wasn't covered in your course. Pretty sure. Does that sound familiar, to have two different sigmas? Other than that probability example we did earlier. Doesn't? Okay. Nope. Good. So what you're going to get is you're going to get an X bar in situation 1 and an X bar in situation 2, and you're going to get an S in situation 1 and an S in situation 2. You're going to get one group of individuals will have a mean and a standard deviation, and a second group of individuals will have their own mean and standard deviation. So these are the sample means in situation 1, and these are the sample mean and standard deviation in situation 2. That's the information you get from your sample. Every individual has a number that belongs to them, and then you combine that information together into a mean and a standard deviation. And then you make a T. And you get to choose how to make your T, and you have two options. You can either make your T this way, like that. Is that okay? You right? Can you tell me what you were asking? Because other people might have the same question and they weren't brave enough to talk about it. Oh, yeah, yeah. Like that? So it is tradition to write it this way. x1 bar minus x2 bar is your estimate for what this number is, and you are comparing it to this answer, which is 0. So technically you could ask, is the difference between them equal to 1.8? And you could put 1.8 in this spot. Yeah. But usually you only ask 0. Yep.
So is there a scenario where it wouldn't be 0 and you would
There is. So you could ask, you could say, my new factory process is supposed to increase the weight of my... Let's just say people are printing textbooks and the customers are complaining that they're too heavy, right? And we're going to create a new factory process, buy a new kind of paper and a new process, and we're going to see whether the weight is less afterwards, right? but I only care if the weight is different by at least half a kilogram. In which case, my null hypothesis is that the difference between the means is 0.5 kilograms. Yeah. And if the difference is less than 0.5 kilograms, I don't care. So it'll be mu1 minus mu2 is greater than 0.5 would be the alternative. That would be a very specific situation. You could imagine doing the other. It's very rare. Most people don't care about that stuff, but your lecturers might think about that. Okay, so this is the traditional one. And you do this in the situation when you don't believe that the two population standard deviations are the same. So this when, if you do not assume the population standard deviations are equal. Now, you'll never know that. But I will say something. You can guess which one to live in. So that's what you do if you don't assume that. Or this. Where SP is, oh man. Well, where SP squared is this. I think that's right. Is that right? Okay.
I don't know.
And this is called the pooled variance. What's that? Oh, the Barbie thing. Oh, yes. It's pooling, Catherine. The butter is pooling. Yeah. I will email you all when it's ready. It won't be in your My Uni for this course because I'm not part of this course. It'll be on the Maths Learning Centre website. Yep.
Do you really do assume that they're equal?
Yes, you can still use the first formula if you assume they're equal, but your p-values won't be as low as they were if you had used the pooled one.
Yeah, but in a exam scenario, if you were to use that one,
They would give you some of the marks because you at least did something that is not wholly wrong. The way to tell which of them to do is to decide if you think the standard deviation should be equal. And most people say that the way to tell that is if one of the standard deviations is more than twice the other one, then you definitely do this one. If one standard deviation is more than 2 times the other one, or sigma 2 is more than 2 times sigma 1, whichever the bigger one is more than twice the smaller one, then you must do this. And that in itself is a hypothesis test, actually. You've done, not sigma 1, S1. If S1 is more than twice S2, or S2 is more than twice S1, if either of those things happen, then you have to do this one. And that's a hypothesis test too. Like we've made a test statistic which is S1 divided by S2, and if it's greater than the critical value of 2, then you make a decision. And so, really cool. And if you do econometrics 2, they will teach you all about that. So, yay! Yeah, econometrics 2 has Econometrics is just a fancy word for statistics. So, yeah. Most of econometrics is regression. More and more fancy kinds of regression. So, the thing is that the degrees of freedoms are different in these two situations. In this one, the degrees of freedom is n1 plus n2 minus 2. And in this one, the degrees of freedom is complicated, but it's usually whichever of these is the smallest, minus 1. Like n1 minus 1 or n2 minus 1, depending on which of them is smaller. And so you get a much bigger degrees of freedom in this one, which means you're further up the t-table, and therefore your critical values are all smaller, and so it's easier to reject. So this one, the degrees of freedom is the smallest out of the two numbers n1 minus 1 and n2 minus 1. And in this one, the degrees of freedom is the total minus 2. There is an official answer for what this degrees of freedom is. It's actually a really complicated formula involving n1 and n2. But the tradition to approximate it is to just pick the smaller of those two numbers. Yep. So if you ask a computer to do a t-test for you, it will calculate something different to this, but you haven't asked computers to do t-tests for you in this course. Rightio. And that's pretty much your list for this course of the different things. So you have, are you comparing two different situations, or you've only got one? That's a decision you have to make. And if you've got two different situations that you're comparing the means in, do you assume the standard deviations are equal or not? Well, thank you. I really have to stop and go home at some point. So I'm going to stop there. Thank you for coming. Don't forget the Maths Learning Centre is open this week.